So, ladies and gentlemen, first of all, thanks again to Gerd and Jan for inviting me here. This was already a very interesting afternoon also for me. And all the speakers before me prepared what I have to say now. And my part will be very relaxing because it's only pictures, no equations, and that's probably the right thing before dinner. Huh? It's about exploring the quantum delocalization and maybe also then collapse models and other things of whatever type we have heard about. And we started this project already a long time ago, in 1999, together with Anton Zeilinger, and since about 2004, this is run by my group. And nowadays we have three different versions of matter wave interferometers that I would like to briefly sketch to you so that you can see what the current status is, but also the limitations and how we can extend that in the future. Of course, we try to get to the 10 to the 6 mass unit range in the next few years, anywhere between 2 and 5, I hope. But everything beyond that will really depend on developments also for space technology, probably. 10 to the 7 is still possible, but you will see that. So, we do high mass quantum interference, where by high mass at the moment our current record is about 10,000 mass units, as you have heard already. And there are two reasons, two motivations here. One is, the question is quantum physics nonlinear. And there's no proof whatsoever yet that this could be the case, but there are interesting ideas and we want to test that. The second thing is, sometimes when I present it this way, people say, well, but I believe in quantum mechanics, so do these experiments make sense at all? Because it could happen that you go on for 10 years and you only confirm quantum mechanics. I would be happy to confirm quantum mechanics. It's a nice theory. But in addition, it's a very useful theory. And that is the second branch of my group, actually out of 3 or 4. Once it works, also at very high masses, we can use that as very sensitive sensors. Actually, in particular, force sensors for all sorts of particle properties. And this is just now becoming very interesting for physical chemistry and molecular biology, so to say, because we use that for measuring internal molecular properties, although we're talking about de Broglie wave interference experiments. And actually, that is the bigger part of what we're doing right now in terms of finances at home. Voila. So, but I promised to show you three versions of doing quantum interference experiments in the quest for nonlinearities in quantum physics. And the simplest thing is, of course, just diffracting matter at material gratings. That's what you would do if you started with your first-year students to think about that. And what you need for that is an experiment that looks very similar to what you know. What you would do in a first-year physics experiment, you need to prepare a collimated beam somehow, a coherent beam, you need a diffraction element, and you need a detector. In first-year classes, you have a laser. A laser is coherent, spatially coherent, and spectrally coherent. And that is something we don't have in molecular physics or in nanoparticle physics, not yet. And so we have to prepare both spectral and spatial coherence by selecting molecules. We have to select them spatially and in velocity space. And the spatial selection, that is done by either focusing a laser very tightly to a micrometer on a source, as you will see, or alternatively, there can be a slit, also micrometer wide here and there, or 3 micrometers wide, to cut out a small part of the wave to prepare semi-plane wavelet. And then this is sent onto the grating, which can be a material grating, optical grating of various types, and at the moment, we still have the material gratings that you will see in a second. And then you need a screen. So, in order to realize this idea, we have the following setup. The molecules that we're interested in, they're coated on a glass surface. This glass surface is the interface between air outside and the vacuum chamber. Of course, we need a vacuum chamber, otherwise collision or decoherence would kill everything immediately, and actually the molecules would not even fly very far under ambient conditions. So this is all operated at 10 to the minus 8 millibars, a little bit more. And the molecules are launched by the laser beam. So they're locally heated with a micrometer spot. They absorb the light, get hot, and evaporate. And they do this with a de Broglie wavelength of about 5 picometers, plus and minus 2. There's a relatively broad velocity spread that we have to select, and we do that by gravitational selection. So there's a tiny spot here, and we have a spatially resolving detector at the end, a slit in the middle, and we choose the free flight parabola to select the velocity with between 5 and 10% selectivity, and that's good enough. So there could be, and there is occasionally, a slit here, slit there, and then the grating. And the molecules that we were looking at were phthalocyanines. These are dye molecules because we can detect them very nicely. But we have a number of different molecules that we were playing with in the very beginning. These were fullerenes, C60, C70, but they do not fluoresce. And here, the nice thing is that we can see each individual molecule. And so the wavelengths I mentioned, and the nanogratings I would like to show here. They were nanofabricated at Tel Aviv University, and they're really tiny, more or less at the limit of what you can do technologically. They're 50 nanometer gaps, 50 nanometer bars, and they're only 10 nanometers thick. So the molecule is only 5 times smaller than the grating is thick. And we're just trying to get to the limit of real graphene gratings, where in the end you diffract single molecules at single atomic layers. So that's more or less the ultimate that you can do. And so we send the molecules through, and you can see what happens. On the detector, we can see each individual molecule arriving. Because we have a fluorescence detection, so an objective is looking at the molecule at the surface, laser is exciting it, and the CCD camera is collecting the light. And then you see, for instance, here these two neighboring molecules sitting next to each other, and they stay on the surface for quite a while, continuously illuminated, and then there are time frames taken with the CCD camera. So this is a time step, time step, time step, time step, and whoops, here this is gone. And that tells us that this is really a single molecule experiment in the sense that we can really monitor when the molecules disappear. And the reason for this molecule to disappear, they're twofold. On the one hand, they bleach, so they may be physically present, but you don't see them anymore. And the second thing is that via the same mechanism that launched them in the beginning at the source site, they can also be evaporated on the detector side when there's too much light. So these are the two reasons, but for us, the important point is that we can prove it's single molecules, and second, that we have a very high spatial resolution. You know that usually the RB diffraction limit gives you lambda over 2 as a resolution limit, but if you have enough signal, and here we do have enough signal, roughly signal to noise of 20, then you can localize this Airy function much better than the width, and here we can typically tell where the molecule is within 10 nanometer precision or accuracy. So that is very good and good enough for all we need, actually also for potential near-field experiments that we plan to set up. So now launching the molecules optically, then sending them through the grating, detecting them on the screen at the end using single molecule fluorescence, we can see the following diffraction patterns. So this is a time frame now seen by the CCD camera. And each red dot here is a single molecule showing up. And so they arrive stochastically one by one, and altogether, of course, they form the interference pattern that you expect. This is a kind of defocusing, so to say, and then you see the interference pattern coming up. This is still a very light molecule, if you wish, only a few hundred atomic mass units. That's nowadays nothing, but still, it's kind of nice, and for pedagogical purposes, it's good. If you wonder why it looks a little bit like it fans out like a hand, the reason is gravity. This is not a quantum gravity experiment yet, but they fall in gravity. And the slow ones, they have more time to fall, and therefore the slow ones at the bottom, they have also more time to spread out the wave functions, to take up the momentum recoil and transform it into position spread, and these are the slow ones and the fast ones. So everything is fine, everything agrees with de Broglie's simple equations, and there's no secret. But this is not, at least we believe, it's not the method to go really to the highest masses, and for various very obvious reasons. As you have seen, we have to collimate the beam very well for the reason that we don't have plane waves from the beginning. And collimating means throwing away roughly 10 to the 8 of all the molecules that we have. And if we think about precious molecules like proteins, but also metal clusters, which are difficult to generate, also semiconductor nanoparticles, the sources will be much, much more dilute, so to say. So it's hard to do experiments this way. The second thing is, which I didn't emphasize here, that when the molecules go through the gratings, they see van der Waals forces. Even though the interaction time is only 100 picoseconds, very short. 100 picoseconds is much, much longer than the femtosecond van der Waals reaction times, typically. So we see very strong influences of van der Waals forces even through this short passage time, and they dephase the interference patterns and make it very hard for very highly polarizable or even polar molecules to go through these gratings. This is why we have introduced two different concepts. One thing is we go from the far field into the near field, and second, we diffract particles at optical gratings. And together we call this the Kapitsa-Dirac-Talbot-Lau interferometer. Kapitsa and Dirac, already in the 30s of the last century, thought about diffraction of electrons at standing light waves, but of course they didn't have any laser, they didn't even know what a laser is. And Talbot in 1836 even started thinking about near-field imaging, lensless imaging of periodic structures, and Lau took this idea up in the mid-50s of the last century. That's the reason for the names. And the setup is the following. Now, instead of using one grating, we use 3 gratings. That sounds like a complication, and actually it is a complication, but it makes life also easier because it's a multiplexing scheme. So instead of using one slit, we can use about 4,000 slits, typically, in the first and the last grating, and that multiplies, so to say. So there's a roughly 10 to the 5, 10 to the 6 gain in transmission, so you get more signal. There's also some loss because there's absorption in the gratings, but altogether it's much, much more flux that goes through. And independent of that, for metrology, so for all these measurements on molecules, this is also a very good scheme, but that's for a different talk. So, but we need some kind of source. For the moment, this is still a thermal source, an oven. Huh? So we heat the molecules here, send them into the vacuum chamber. In this case, it's 10 to the minus 9 millibars. Again, there's a velocity selection, a gravitational velocity selection by slits, so no mechanical rotating or vibrating parts, just a passive selection. First grating is again a mechanical grating, a bit thicker than before, 266 nanometer period, the same here. The third grating is a standing light laser wave. And what the laser does is it creates a periodic structure of nodes and antinodes, of course, and the electric field of the laser polarizes the molecules, and so they have a dipole moment, and dipole moment times electric field, that's an energy. Energy is related to phase, so there's a phase imprint, a periodic phase imprint here at this position, and that transforms in a density structure a little bit further downstream. And then we have to detect this pattern, as you will see in a second how we do that, and detect the molecules in the end in this case, it's an electron impact ionization quadrupole mass spectrometer. But we have actually on these parts here, detection and source, we have worked on 5 and 6 or 7 different methods, and we combine them in various experiments. Now, the kind of cartoon how this interferometer works is we start from an incoherent source. So there's no phase relation between the molecules. How could it? So there's none. So we have to prepare each individual molecule in a state that it can delocalize and do quantum things. And so we send them on this first grating, and in the first grating, they're confined in each individual slit. So each molecule passes through one slit. And one slit is kind of the origin of a semi-Huygens wavelet, if you wish. Huh? So they start out, and the wave function expands. And the structure is made such, and the distances are chosen such, that the wave function spreads out over at least 2 or 3 neighboring nodes and antinodes, so that there's a delocalization across strong phase shift, no phase shift, and that transforms into, finally, in a distance which we call the Talbot distance, it transforms into a molecular density pattern. And this density pattern is a quantum structure, if you wish. The visibility of this structure, that is the telltale sign, so to say, of the quantum nature of the molecules. For that to happen, it's important that this is close to the Talbot length, which is given by the grating period squared divided by the de Broglie wavelength, which is a few picometers again. Actually, in these experiments, we can go down to 200 femtometer de Broglie wavelength, so that's really tiny. As you can imagine, the molecules have only a few nanometers diameter, and the de Broglie wavelength can be 200 femtometers. Now, in order to see the nanostructure here, one could, again, use the trick of before, capture everything on the screen, look at it with a microscope. We haven't done that because, for historical reasons, actually, and for alignment reasons. But you can as well take the third grating and scan that, and then count whatever goes through. And if you do that, you see a periodic structure, which is our quantum interference pattern. Now, if you don't believe in quantum mechanics, then of course you could say when you look through two hands, you would also see stripes, periodic stripes, and they would be moire fringes, nothing to do with quantum mechanics. So what you have to do is you have to make sure that the fringe visibility really agrees with what you expect and disagrees, quantum mechanically, and disagrees with classical physics. And that is what we've done for various molecules, which I will not show all of them here. So I will just focus on two record holders, so to say. And the first one was the molecular octopus, as we call him, because it's a carbon nanosphere with 8 arms of perfluoroalkylated carbon chains, so to say. That's already a pretty massive thing, which is as massive as an insulin molecule, just to have a reference in the protein world, with 356 atoms. And this shows very nice interference fringes, actually 50% contrast, as much as we expected. And then we have to do this trick comparing quantum and classical fringes, and so we have to vary something and see how that changes. And what we can very easily is we can change the phase imprint by cranking up the laser power. So more laser power, more phase shift, different fringe visibility. And we can compare that to the quantum and classical case, and well, the blue curve is the quantum curve, and the experiments are well in this range. Signal to noise here is not super duper, and the reason for that is we have only a few milligrams of this compound. It was actually, and there's not more in the world, so to say. Huh? These molecules are made for us to fly very, very nicely. Huh? Same with this guy. This is currently the record holder. It even doesn't have a name because it was just made for us. But this has 10,123 on average, of course, because in practice there's a huge isotopic mass distribution. Not huge, but there's a distribution. But they have already 800 atoms in one single molecule, covalently bound. And again, this shows a very nice quantum interference pattern in agreement with our expectations. 800 atoms is already as much as typical small BoseEinstein condensates nowadays would have. But the contrast is that these guys here survive at 500 Kelvin internal, external temperature. So this is really a classical body, if you wish, but prepared in a state that it acts quantum mechanically. Actually, we had a very hard time publishing this because the chemists didn't believe that this could possibly work. Huh? But it does. Huh? So we didn't cheat. These are real measured data. Huh? Voila. So we are currently trying to get to higher masses, but for that, we have again a different interferometer scheme, as you will see in a second. Just to compare to something biological, this is cytochrome C, also protein, similar size, similar mass. But here it's much harder to do experiments with these things. That's why we now have projects to work on that. Proteins do not want to fly so easily, more difficult to detect. This is a big experimental challenge, but once it works, it would be really great for metrology. Now, last but not least, we have a new interferometer. So every few years we change. Thank you. For expanding, so to say, the range of possible experiments. And this is now one that works with only optical gratings, optical ionization gratings. And it's called the OTM interferometer, like the optical time domain ionizing matter wave interferometer. The simple idea in quotations is that we take the Talbot length of B4, which was crucial for setting up the near-field interference, and divide by velocity. If you divide the length by velocity, it's a time. So we end up with a Talbot time, and this Talbot time defines now a time between pulses where interference should occur. And the crucial thing is, again, that the grating period shows up squared and the mass of the particle. Now, the idea was to set up something which is universal, which acts on a very wide class of particles, and it's, in this particular case, an ionization grating. So we take a 157 nanometer laser, which is a fluorine laser, which can ionize metal clusters, organic clusters, all sorts of things, dielectric clusters. And wherever the clusters pass the antinodes, they get ionized and are extracted, so it's an absorptive grating. And in the nodes, they can pass through, and it's like a slit, an open slit in a mechanical grating. But it's not a mechanical grating, and therefore it cannot clog, it cannot be destroyed. It's extremely regular and good. So a very crucial number is to see, well, if you take the Talbot time here, it's 15 nanoseconds per atomic mass unit. So for a single proton, the separation between subsequent pulses should be 15 nanoseconds, which is very short. So we don't do experiments with hydrogen. At the moment, we do experiments with particles in the 2,000, few thousand mass range. But if you want to go to really high masses, 10 to the 9 or 10 in the end, this is 15 nanoseconds times 10 to the 9, that's 15 seconds coherence time that you need. But that's actually true for all the experiments that you can envisage and that other groups also envisaging. So you need very long coherence times for these collapse tests in the end. The experiment looks like that in practice. We have a source, whatever nature this is right now, then 3 gratings, 3 lasers, VUV lasers that can only propagate through vacuum or helium or nitrogen, but not in air. And the idea is that we prepare clusters of, in this case, anthracene molecules, which fly in front of this mirror, and whenever the first bunch arrives, we switch on the laser. The laser ionizes in the antinodes. Then comes the second and the third, so there are again 3 gratings, but these 3 gratings only exist for nanoseconds, 8 nanoseconds each, and currently with a time separation of 20 microseconds roughly. So at the end of the day, there should be an interference pattern here, which is very hard to see in the time domain, so you have to do something to make that visible. So we pass the molecules on to a time-of-flight mass spectrometer, where they are detected with time resolution and with mass resolution. So that ends up here as a mass spectrum. Now, in this mass spectrum hidden, there's the quantum interference, and you will see in a minute how that works. So if everything is set up properly, and if quantum interference occurs for the symmetric case of the pulses, so when all the distances correspond roughly to the Talbot time, then we should have a higher transmission. There's a kind of resonance, a Talbot resonance, which is due to interference. And if there's an asymmetric configuration, even so slightly, 100 nanoseconds difference between left, right, and first and second and third is already sufficient to destroy the interference pattern. It's very narrow, this resonance. So in comparing the symmetric and the antisymmetric or asymmetric case, we can get a signature of this interference. So for one particular cluster, so we form anthracene, that's anthracene, and they cluster to up to 8, 10, 12, whatever, not even the odds, also the evens. So all the clusters come up, and we look for the transmission after this interference pulse sequence. And here for anthracene 10, you can see a resonance enhancement. For anthracene 8, there's none. They have the same transmission. And now you can plot that for all the different masses that there are in the cluster beam, from trimers up to, well, the decamer would be here, so 12, 13, and so forth. And the wavy structure that you see here on top, that is actually the interference structure. So the Talbot time makes that, and the Talbot resonance makes that quantum interference enhances the transmission here and makes more clusters go through these 3 grating arrangements. The same here for half the time. And when it's off resonance, so to say, it does not enhance it. And of course, this is not yet a mass record. It's just a demonstrator experiment. But the principle of this experiment is that you should be able to talk to metal clusters, to ionizable organic molecules, to silicon clusters, whatever. And now we're again working on sources for making this happen. Just to conclude, because I think I have to. there's an intrinsic limitation here on the ground for doing these experiments, but that's actually true for all experiments of this sort, where you need free-flying particles to see quantum delocalized wave functions. In our case, a typical length of the setup is given by the Talbot length. And I mentioned already it's g squared, the grating constant squared, divided by the de Broglie wavelength. So a typical smallest grating period that we could possibly do is 100 nanometers. Of course, you can think of structures which are smaller than that, but if we talk about particles which are 10 to the 9 mass units massive, they have 50 nanometers diameter in gold already, so they would not go through if the structure was significantly small. So roughly 100 nanometers is a good number. That's actually true for many competing ideas as well. Then the question is, what is a typical, what can we easily prepare, what velocity can we prepare, because that determines the de Broglie wavelength. There's no laser cooling for big things, except for cavity cooling, which we also succeeded in implementing just right now a little bit. But for really massive throughput, we thought it's better to put numbers in which are buffer gas cooled, helium buffer gas cooled particles. And if you just take standard buffer gas cooling temperatures, you find that, well, a picometer de Broglie wavelength would arise for 1 million mass units and 15 femtometers for 10 to the 10. Now, I mentioned already that currently we can operate with 200 femtometers de Broglie wavelengths, actually in both experiments, both near-field interferometers. So there's only a tiny factor of 10 in terms of de Broglie wavelength to be bridged to get to 10 to the 10 mass units. Naively, you could say, why not just stretch the interferometer by a factor of 10? Currently, it's 5 centimeters, make it 50. It still fits into the lab, no problem. But you also have to look at the coherence times that are required for the wave functions to spread out. And again, that's for all the groups that are interested in these things, currently the limitation. You need about 30 milliseconds coherence time for 10 to the 6, 3 seconds for 10 to the 8, and 300 seconds for 10 to the 10. This can be done on Earth, probably 10 to the 7 as well. This is a drop tower, maybe in Bremen or Hanover. This probably requires microgravity, and that's why a number of people is interested in setting up a mission for space, but this costs actually 500 million or so. And that's space costs. So that we cannot promise on a very short time scale. Anything on the 10 to the 6, 10 to the 7 mass unit scale is in near range compared to all space things. And with this, I conclude, since I have to, but whoops, so we'll skip all that. Just to summarize briefly, so that's what we have in the lab right now. Far-field diffraction, near-field interferometers, 2 different versions. This is kind of the most pedagogical thing at the moment. This is the highest mass, actually, in the world, so to say. This is a very promising future setup for high mass experiments. And with this, I thank you for your attention.
These are nice experimental results. Can I say that I have a real problem with interpretation? The reason is, so I'm a half chemist, and we calculate these molecules all the time, basically. And we have this nice theorem from 1964, which we use to calculate these things, which says that the electronic density is all we need to know about a molecular system to have all the physical properties. The de Broglie wavelength is not a physical property in this respect. So then, let me be positive about it. I think actually what you might measure are interactions, which are quantized. And as far as I can see, your molecules were all polarizable. Is that correct?
I may answer in 2 words. First of all, I disagree with your first statement. Of course, the electronic properties are very important if you want to know.
There's a theorem out there, mathematically proven.
No, that's not true.
So what?
I mean, this is not true for the translational propagation of the molecules. It is true. No, kinematics is not dependent on the internal state. It's like if you're sitting on a rowing boat on a lake, you're yourself.
Functional theory says it's true even if it has a velocity.
That's nonsense. But
90% of all the calculations are done with density functional theory.
The DFT is absolutely right for the internal structure, and we need that. That's true. But for the translational motion, of course, that's completely irrelevant. And you're absolutely right that the polarizability is very crucial. It's important for the interaction with the light gratings, with the mechanical gratings, and then we calculate these things, of course, as well, with Gaussian and other things. So,
why not try it with a non-polarizable molecule? Why not cool down the system? Why not try to actually isolate the effect? What I see here is actually a mixture of many different effects. We, in solid-state physics, we try to isolate a single one. Why don't you do that?
It is isolated, that's what I want to say. The internal state plays no role. We explicitly did experiments to go from the isolated property to coupled properties, and you can do that in fullerenes by heating them explicitly to high temperatures using laser light. And then, of course, we lose interference. That's normal. But you have to see that the emission rates, the only thing that can act on the momentum state is exchange of momentum. So if you don't scatter light, if you don't scatter molecules, there is no perturbation of the de Broglie wave function. So all the internal states are decoupled, unless you couple them, and you have to heat that in order to get that.